For this particular webinar, we're going to go through a few things. We're going to talk about grain bin challenges and considerations. What are the facility components? What are some things to consider when you're evaluating the construction of a project? What type of traditional foundation support are you offering, or is the geotechnical engineer offering in their reports? What pros and cons are associated with them? Is ground improvement an option? What are the advantages for the Geopier system that can support your grain bin or your facility? We're going to talk about the methodology, a brief overview that goes into Geopier design, and then some local contacts for you to consider if you'd like to know more about this type of application and the ground improvement systems that we talk about briefly in this presentation. So why are foundation soils important? You know, these things are supporting these large structures, and they keep getting larger and larger as we go along here. They used to be 30, 40 feet in diameter, and now we see very large structures, some in excess of 125 or 150 feet in diameter, with eave heights that keep creeping up past 100 feet in the air. This exerts a large amount of pressure on the foundation soils, and this can have an effect if you don't properly reinforce the foundation soils. If you see in some of these pictures, you can see some of the effects if you don't consider a soft ground or a soft zone underneath your bins. You can see some of the welding that may break, or you can see some of the stair towers or some of the conveyance systems that may not interact with the grain bin as anticipated. That could mean for some issues for the handling within the grain bin and also the facility operation as a whole. If you notice on this picture, you can see that this bin is tilting to the right. So it's off center, allowing for the grain bin maybe not to operate as intended. So you significantly strain the stresses within the grain bin. So it may affect the loading and unloading cycles. Within the structure itself, you may see cracks develop if you haven't addressed the foundation soils appropriately. If you have non-planar settlement or differential settlement across the bin, and it's not planar, then you may have cracking within the tunnel floor or the tunnel ceiling if you have an above grade tunnel or below grade tunnel. So let's talk about grain facilities as a whole. There's a lot of stuff going on in this picture. There are a lot of conveyance systems, both in the top and the bottom of the structures. There are towers in between grain bins. There are large grain bins themselves. And there are a lot of things interacting here. These high grain bin pressures is a big design component of this. Not only that, the deep influence that these grain bins and overlapping stresses account for below in the soils, which we'll talk about here in a minute. Deep pits, there are oftentimes deep pits and elevation differences between the grain bin, the associated pits right beside them. Sequencing is important for certain excavations, so it's backfill of those excavations. Tower uplift requirements, and you can see here in between the two far right grain bins, there's a tower in between. Are you addressing the uplift requirements within the tower from resistance and overturning because of how high it is in the air? It's necessary to make sure that those design considerations are taken into effect. Most of the times, these grain facilities are located next to a rail line. So settlement control is critical to make sure that the rail line doesn't go anywhere, to make sure that settlement control of the adjacent rail line can still is not an issue, and you can still maintain the rail line as intended. Then also conveyance systems. Both at the top and the bottom of the structure, it's important that the grain bins interact with the conveyance systems as designed. There is some play in these connections and allow for some movement, but you want to make sure that that movement is within tolerance. As far as the layout from an owner or designer, this is a typical layout of what we see in our office. We may see a layout like this where there are two grain bins that are going to be constructed. They're on the right side of the screen, but then they also have a future expansion that may happen in a later year. The dash line to the left and also the ones at the bottom, if south is located at the bottom of your screen here, you can see that the addition of these future bins will be considered so that you can still use the pits and all the existing facilities for the two that are going to be constructed in this phase. What bin diameter will the new bins be? What eave height will they have? What is the bushel capacity? Will there be reclaim tunnels going below grade or above grade? That's important to consider. Then also the adjacent pits, which we'll talk about here in a second. The site under construction, site history is important to know what is going on with this particular site. The geotechnical engineer will do a great job of understanding the soil conditions relative to the performance of the grain bin structure that you're planning on putting on that site. However, any site history is also important to evaluate, meaning, are there underground utilities? Were there previous structures within the footprint of the grain bin? Or are there any previous structure performances that have caused issues in the past, either structurally or geotechnically speaking? Did you have a grain bin located on this site that experienced too much settlement? If so, what was done? Was it supported on the native ground? Was there another system that was implemented below it that maybe didn't work as intended? These are things to consider when you're moving forward with a new project or a new phase of an existing project. Adjacent pits and elevation changes. You can see here on this picture that the far right represents the end use condition. Well, what's really going on can be seen in the ring wall elevations of elevation 100 feet, and then right beside it, there's a pit that's located 25 feet below where that ring footing is going to bear. The ring footing stresses on the adjacent pit need to be considered both structurally and geotechnically speaking. Need to make sure that the ring footing that's going to be imposed at a higher elevation, when it imparts stresses on the lower pit, that the walls are adequately designed. And similarly for the truck receiving pit, it's also at a split elevation between the two on the north of your screen or on the upper portion of your screen. It's important to consider the sequencing of how these things will be built. They look great on a boring location plan or on a preliminary plan, but how will they be constructed? Those are things that are key to understanding how everything will go together. As far as reclaimed tunnel considerations, there are two types within the industry that I'm aware of. There are above grade tunnels, which is on the left, which you can see is located with a stem wall or a concrete stem wall. Then the corrugated steel bin will go on top of that, or a below grade tunnel, which is on the right-hand side of your screen, meaning an excavation will be required to get the below grade tunnel installed. Now, with the Geopier system, which we'll talk about here in a little bit, there are considerations for both. All the Geopier elements will be installed from existing grade, meaning the top of the purple elevation. However, when they're installed from the top of the purple elevation on the below grade tunnel, you may need to excavate a portion of the Geopier element, as long as this can, and that's the gray zone that you see on the right part of your screen. If the Geopier elements are excavated out, as long as the material going in is a well-graded crushed base stone, compacted in accordance with the geotechnical engineer specification for compacted structural fill, the grain bin will still be able to perform as intended. So this is not an issue. As far as these grain bins are concerned, typical diameters range from 48 feet to 136 feet. You can see here that there's an above grade tunnel located in this figure, and you can see that the infill, located in gray, needs to be accounted for in the pressure on the foundation soils. Typically, we see bin floor loads up to 7,000 PSF, which is a honking amount of load. We'll see this pressure applied to the bin floor, where you see the words bin floor. However, the pressure on the foundation soils needs to be considered with the infill plus the bin floor pressure. Now, settlement on the order of 3 to 6 inches is typically okay. However, it depends on the specifications from the bin manufacturer and also from the foundation engineer. You need to make sure that everybody's in lockstep regarding the performance of this bin. There are a lot of different components to have into consideration. It's necessary that everybody is coordinating on the same time, so being involved in the design team is key. Differential settlement on the order of 3 inches is typically okay. However, the same rules apply. It all depends on what the specifications are for that particular bin that's being constructed. As far as the stem wall infill goes, it's typically 4 to 8 feet in thickness, generally speaking. This allows for an above grade conveyance system. You add that pressure from the infill to the slab pressure, as I just mentioned. The high stem wall loads from grain arching require settlement control, and we'll talk about that here in a second when you see some figures. Wall loads of 20 to 60 kips per linear foot are common. However, we have seen higher, the higher the bin height. Some of the information that I just mentioned as far as bin pressures can be estimated from information from these bin manufacturers. A few are shown here, and the information exists on their website and also within literature that's available at national conferences. This information can help you and help us estimate the amount of pressure that we're going to see on the bin floor. That's important because it allows us to understand what the capacity of each element will be if a ground improvement system is required. If you take that information that's available either on the website or in literature, you can see that information and apply it to this type of procedure where you can say, okay, Mr. Owner, what are you going to store within this grain bin? You can see in the upper right-hand corner, you can see different bushel weights. The reason this is important is because it allows us to see what pressures we're going to see within this bin. If the bin is designed for sunflowers at 25 pounds per bushel, but then all of a sudden we know that soybeans is going to go in here as 60 pounds per bushel, that's a big difference in load. It can have a huge effect on the amount of settlement that you're going to see based on the amount of demand that's currently in the bin. Similarly, we see an angle of repose. That also goes into effect as far as when the grain gets dropped from the top of the grain bin down into the grain bin, it will form an angle of repose within the structure. These angles can be seen here on the middle part of your screen. That information is also taken into effect to see what the total pressure is going to be in blue on the slab, which is an elevated slab for an example. So when we're talking about pressures, I mentioned a couple of times that the purple, or that the stem wall infill pressure, which is located in purple here, needs to be added to the slab load, which is shown in blue arrows. You add those two up to determine what the pressure is going to be on the purple stratum or the foundation soils below the bin. Also, I talked about the grain arching to the walls due to friction. That in turn goes into a ring wall load that's indicated in red here. The design, be it from a shallow foundation support or deep foundation or ground improvement, or we're going to rely on this type of information to make sure that the spacing of the elements or that the foundation soils can adequately provide support for these red loads that are transferred to the ring footing down below. Okay, let's get into geotechnical boring and cone penetrometer test information. I'm going to spend 2 slides talking about geotechnical information that can be beneficial when you're looking at your projects. Bins and tanks continue to get larger. So with the size of these keeps growing in diameter and also eave height, it's important that the geotechnical exploration follow suit. Adequate coverage across the bin footprint is important. I mentioned differential settlement is key on these projects to make sure everything operates efficiently. Well, getting borings and cone penetrometer tests with adequate coverage around the perimeter as well as in the center is important to make sure that you have those conditions covered to make sure there's not a soft layer down there that we don't know about. The scope depends on bin size and geology. A local geotechnical engineer that you work with can provide this information to you and provide a scope for your project. At least one of the borings or CPTs, the center is usually best, needs to extend deep enough to determine the compressibility of the soils. We'll talk about the 2 zones here in a little bit about the upper zone and the lower zone. The lower zone meaning the portion below the bottom of the piers. That's the key to determining the compressibility of the lower zone, is to make sure that the borings and the CPTs extend deep enough to evaluate the compressibility within that zone. We'll talk a little bit about that here in a minute. As far as the geotechnical lab scope goes, there are several index testing or several lab tests that can be performed at minimal cost to the geotechnical exploration cost or scope. Moisture contents and Atterberg limits can give us a good idea for the compressibility of both the upper zone and the lower zone soils, and they're very beneficial to adding clarity on the compressibility of these soils. Grain size tests can also be beneficial as well. This be a wash 200 or a full grain size with hydrometer. There are different options available for the grain size test as well. More advanced testing can consist of consolidation tests. I mentioned a little bit ago that the influence of these grain bins drives deep into the profile. It's sometimes necessary in certain geologies to make sure that you have that compressibility identified and that you have the adequate lab testing within that zone to make sure that you're properly estimating the amount of settlement that you're expecting under the applied bin loads. As far as total settlement is concerned, this is a typical settlement profile for a grain bin, although it could be a flatter curve, I guess, depending on the nature of the geology. But bins are typically designed for 2 to 6 inches of total settlement. If you have a soft soil there in lighter orange, you may see this profile. Differential settlement is typically versus the perimeter versus interior, but can also be from one side of the perimeter to the other side of the perimeter. Because these things are going to act in a planar manner, typically it may be from one side of the bin to the other, as seen in this picture on the right-hand side. Typically, these specifications for differential settlement are given from the bin manufacturers. They will have a tolerance. I've seen several bits of information within literature that say, hey, the maximum we can see from one side to the other is 3 inches. This allows for the sweeps to be able to work appropriately or properly. And so this is our design criteria. But they also need to make sure that the total settlement is appropriate as well, because all the connections at the top and the bottom are important. So there's a lot of things to consider here. These are just a few to mention them to you today. Okay, so we have our borings, we have our cone penetrometer tests. What are we going to do with this? What is the geotechnical engineer going to do with this stuff? It's got all these little squiggly lines on CPTs. It's great. Tells us where a hard layer is. Great. How are we going to support this bin? They'll go through a variety of options. They'll say, okay, the holy grail. Can we support this bin on nothing, on just native soil? That's great. Don't have to do a thing. Awesome. But if they don't have great soil, maybe they need to replace a little bit of that material, make it less compressible underneath that grain bin, and really compact that material in and less compressible, but it's highly compacted and all that kind of stuff to then support the bin. Or let's say we have slop or very soft clay or very, very loose sand or something like that. We have to transfer a load down to a competent bearing stratum. That's going to be in the form of steel H piles, auger cast piles, drill shaft, pipe piles, all this kind of stuff. You have those deep foundations available to you. So that may be the most appropriate solution for your bin. Some of the pros and the cons of shallow over excavation and replacement are like this. Let's see, some of the pros can be you're using local equipment or contractors with local labor. That's a pro. Stuff is locally available for use. This could be from a co-op, from people within your community, so on and so forth. That could be a key benefit. But some of the cons could be, what if you have to install a bin right next to an existing one? Do you have to use temporary shoring in order to make way for this over excavation requirement? Also, what if you have shallow groundwater within your soil conditions? Let's say you have to get down to 12 feet, but groundwater's at 7 or 8. Are you going to be able to get down to the depth without dewatering, or are you going to have to draw down that water level to make sure you can make the over excavation depth appropriately? And some other things are, can you achieve the right bearing pressure with this soil? I mentioned bearing pressures of about 7 KSF or applied pressures of 7,000 PSF. Are you going to be able to provide that 7,000 PSF bearing pressure just by over excavating and replacing that with a less compressible material? Okay, so deep foundations, let's talk about this for a little bit. Excellent settlement control. If you're transferring the loads from the grain bin down to a competent bearing stratum, you're going to see settlement on the order of an inch or less, which is awesome, which is great, works well. Very heavy structures. Local contractors and labor can be used for deep foundations or local within the state. That's usually not an issue. There's usually no depth limitations. Up in the upper Midwest, we have the Lake Agassiz clay deposit, which requires driven pipe piles to go down to about 100 or 150 feet. That can take a huge hit on the construction schedule and also the cost for the project if you have to do that. That's just an example. That's not to say that, that's not to say that pipe piles shouldn't be used there. I'm just putting it out there. Let's talk about pile caps and structural slabs. That's a huge cost for a project of this size. Usually these things are 100 to 135 feet in diameter. That's a really large pile cap or structural slab that's required to support this grain bin. Slower installation speed could be a day to construct one element if it's a drilled shaft. Additional time required for pile cap prep. There's a lot of steel and a lot of concrete to tie up and deliver to the site. That could have a huge effect on your budget and schedule. Let's talk about the rammed aggregate pier system as another option that may or may not be in your geotechnical reports. It's necessary to evaluate a solution that will keep within the bin supplier's settlement specifications. This being 3 inches of differential settlement from one side of the bin to the other, or something else as far as total settlement goes. Support the bin on shallow spread foundations by using the rammed aggregate pier system. This allows you to eliminate the use of a pile cap, thereby saving time and money associated with the preparation of that. Because you're creating a densified crust or a stiffened crust, you can allow for higher bearing pressures. This reduces the footing dimensions, making them smaller for the ring walls or ring footings. And you can minimize differential settlement between the new bin and the surrounding structures. This helps with conveyance systems and other connecting structures. As far as cost savings, the equipment can be set up in a matter of hours once it rolls off the truck. We're ready to go if the site is laid out. As I mentioned, there's no pile cap or grade beam required. Temporary shoring is also not required. Generally, with over excavation and replacement, there's a 20 to 40% cost savings when your depth of over excavation and replacement is 5 feet or greater. The most important thing I think we found on several projects that we've worked on is it keeps the adjacent facility fully operational. This is important, especially at harvest time. Everything must remain operational. We've heard that from a few folks that we've worked with. As far as comparison to deep foundations, there can be a 20 to 40% cost savings realized over deep foundations. On this plot here, you see pile length on the x-axis and pile capacity on the y-axis. As the pile lengths continue to get longer and the capacity tends to get lower, the benefits for cost savings increase for using the rammed aggregate pier system. On the other side, if you have a short pile length and a high capacity, then it may be a job for deep foundations, or the wrap cost savings could decrease as far as the added benefit. As far as where the rammed aggregate pier systems are added, you'll see here in this picture that they're located throughout the entire bin. This is to add a stiffened crust underneath the bin to help with total and differential settlement, while also providing high bearing pressures for the ring footings. As far as the specific systems that we're going to talk about today, I'm going to focus on 2, although I'll introduce you to all of them. The GP3 system is a drill and fill system similar to the X1 system. We'll show you videos of the installation methods on those 2. And we'll also, I'll just briefly talk about the Rampact and Impact systems. Those are displacement systems, and you can see that there is a hopper on the Impact system and another hopper on the Rampact system that allows for rock to go through the mandrel to be delivered at the bottom of the mandrel and extracted that way. These are for caving sands, soft clay profiles that are subject to caving, where casing cannot be used with the drill and fill system. So let's get back to the GP3 system and the X1 system, which are drill and fill type technologies. We'll show you some of the installation methods with these 2 technologies. The Geopier system consists of 3 different pieces of equipment. See a Geopier drill here on the left, Geopier tamper on the right, and then a skid steer to deliver rock, sand, or recycled aggregate to the hole once the cavity is drilled. Now, there may be a 4th person, that may be a foreman, or another skid steer that might be taking the spoils away from the holes as they're drilled. Rapid installations, typically 20 to 100 piers per day. That's a wide range because it varies from site to site. This can have an effect on groundwater conditions, how deep the holes are, just soil conditions in general. There's a lot of different things that can help with the installation of the rammed aggregate pier system. As far as the installation process goes, you excavate a cavity, and then you dump a lift of open graded aggregate within the bottom portion of the cavity. The bottom bowl open graded crushed rock pre-stresses and pre-strains the soil. This builds a good compaction surface to provide dense subsequent lifts. The subsequent lifts build up lateral stress in the soil. The more confinement you have, then the more load you can apply to the pier and the less compressible the geopier zone becomes. The vertical ramming process and the installation of the geopier elements creates a stiffened crust, as I mentioned before, to reduce the settlement within the geopier zone. This helps with achieving higher bearing capacity within the ring footings and within the crust, thereby allowing for reduced ring wall footing widths and settlement control. Once you see that the subsequent lifts are compacted, the first one, then you continue all the way up to the surface. X1 construction is similar to GP3, same type of profiles where pre-drilling is required. However, the reach of the X1 system is much greater. You can see here there's a mast rig on the bottom left-hand portion of the picture, and you can see that the depth is pretty great. You can go to about 45 or 50 feet. There's no tripping in and out of the hole, and I'll show you a little bit about the chamber itself here in a second. But the rapid installations are key to the X1 system. An X1 pier to about 45 or 50 feet can be installed in about 10 to 15 minutes. That's important if you have several long X1 piers that need to be constructed for the support of the bin, which is usually the case. As far as the chamber goes itself, these are some of the pictures of what the chamber looks like itself. These chains that you see located around the outside hoop as well as the centerpiece allow for a valve to be present in the bottom of the mandrel. What this does, this allows the rock to flow through the chamber when it's on the upstroke, but when it's on the downstroke, it forces a compaction surface to allow that rock below the chamber to force out into the matrix soil, thereby building the pier. This is the next one installation video. You can see the auger pre-drilling the holes on the right. The mandrel is lowered down into the hole. Rock is then added to the hole for the bottom bulb. It'll get down to depth, and then we'll continue that process until the subsequent lifts are built all the way to the surface. As you can see, the rock flows through the chamber and compacts the individual lifts. It just repeats the process until it goes all the way up to the surface. And you can set your ring wall footing on top of it. This is the finished product here. Okay, let's talk about a little bit about the design methodology that goes into supporting grain bins. The zone is divided into two zones called the upper zone and the lower zone. The upper zone represents the pier zone and one bowl diameter below the bottom of the shaft and its compressibility within that zone to estimate a specific amount of settlement within that upper zone. They'll then combine that with the lower zone, which you can see here on the right-hand side of your screen. The two are added together to see what the total settlement is and also what the differential settlement will be for this grain bin so that we can see if it meets the manufacturer's performance criteria for this grain bin. Typically, we see the borings or the cone penetrometer test need to extend deep within the profile because you can see here that the zone of influence is very deep. If B represents a diameter or an equivalent square, you can see that borings or CPTs would need to extend to twice that depth. Now, that's not saying that all borings and CPTs need to go to that depth. If you hit a hard layer or a very, very hard layer like weathered rock or very hard glacial till or something like that, additional exploration below that elevation may not be required. So you may not need to go to 2B. The Geopier capacity is selected and a trial shaft length is selected when talking about the Geopier design approach. A square spacing is determined by taking the square root of load capacity of a Geopier cell. This is both the pier and matrix soil combined, the load that square is going to take, divided by the applied pressure. Now remember, this is the stem wall infill and also the pressure added together to see what spacing needs to happen in the middle of the grain bin. You evaluate the settlement of the upper zone using Hooke's law. This is the applied pressure times an influence factor. This is typically a Boussinesq influence factor times the height of the upper zone, which can be just the shaft length itself, divided by the composite elastic value here, using this equation, which is a function of the area ratio and the properties of both the matrix soil and the pier. And it's worth pointing out that the piers are allowed to strain more with this type of application than normal building foundations. The reason for that is the settlement criteria for these is typically different. You may see settlement on the order of a ½ inch to an inch for typical building support. However, as we've discussed in this webinar, you may see total settlement on the order of 3 to 4 inches. So allowing for additional strain and allowing for those values to be included within your equations allows for economics to be gained and wider pier spacings to be used. The lower zone settlement is calculated using conventional geotechnical settlement analysis. So on the left-hand side, we have elastic modulus values, which can be from SBTN values and correlations, or we have the right-hand side, which is consolidation theory. So therefore, when I mentioned, when we were talking about lab tests, obtaining consolidation tests within the lower zone, this is what I meant. Can we get a consolidation test within the lower zone soils to evaluate the compressibility? Or will these soils, which will likely see large bend pressures from 6, 7 KSF, if we see that high of a bend pressure, will these soils behave normally consolidated, or will they behave over-consolidated, or a mixture of the two? This equation here accounts for both, where you see C epsilon R on the left and C epsilon C on the right. It's important, if you're in specific geologies, to evaluate the lower zone compressibility. If the materials underneath the bottom of the pier zone are not stellar, let's say, then consolidation tests may be required. Okay, we've already talked about the deep effects of the width according to the width of the grain bin or the equivalent square and the depth zone of influence. But this kind of summarizes what's going on. You have the upper zone compressibility within the pier zone that we will test via a modulus test, and then there's the lower zone component, which is the portion of this that we will not test until the bin is loaded up. So when we talk about the importance of geotechnical exploration, this slide is important because it shows you, okay, we can test the upper zone, but do we know everything we need to know about the lower zone? Or do we need a little bit of additional information? And this information may happen as the scope is determined at the beginning parts of the proposal, or it may be, hey, we uncovered some soft stuff down at 30, 35 feet. I think we need to get a Shelby tube here and get a consolidation test running. That's an active dialogue that will happen as you're drilling the site. Okay, as far as overlapping stresses are concerned, let's say that we have two bins that are going to be constructed at the same time. These stresses will talk to each other underneath the ground. I'm not sure what form of communication, but they will talk to each other underneath the ground, as you see here. So typically you would see these stress contours start to overlap when you have two grain bins that are going to be constructed at the same time. And typically this adds about a ½ inch to an inch in between the grain bins. So there at the center, you may see 2.5 inches, but at the far left or the far left edge, you may see 1.5 inches. So when there are two grain bins going to construction at the same time, you'll see overlapping stresses here in the middle part, which can be accommodated in the design. This is a profile and plan view of what a typical Geopier ground improvement solution looks like. You can see at the top, you can see the ring wall footings supported right on Geopier elements. And the Geopier elements are installed from existing grades. You can see that these will provide arching for the aeration floor, whether it be a quad F or a quad H or whatever type of aeration floor you have. These will provide uniform support of these aeration floors. You can then see the piers located directly underneath the tunnel. Those are located here. So you can see the profile view here, and you can see the plan view here located underneath. And the same thing on the other side. Okay, let's shift into talking about rigid inclusions. Specifically for grain bins, I'm going to focus on the geoconcrete system, which is on the right-hand side. However, we have several options available to discuss with you should you want to know more about the grouted impact system or the armor pack system that's not mentioned here, or just know more about the geoconcrete system here. We will have installation videos of both the GP3 installations and the GCC installations that you can see in the following slides in the case histories. As far as the installation equipment goes, you can see on the left-hand side, you have a mast rig. This has a reach of about 55 or 60 feet. The mast rig will attach to either the concrete boom truck, which you see in the bottom, or a line pump, which is in the upper portion of your slide. Once the concrete is attached to the boom truck or line pump, it'll then be connected at the top of the mandrel, which you can see in the upper right-hand corner. This is a closed system. The closed system is not open to the atmosphere or anything like that, but the concrete is pumped directly into the mandrel. The bottom of the mandrel can be seen in the bottom right-hand picture. This acts as a valve, the same way that we talked about X1, and you saw down into the chamber where the chains acted as a valve. You can see that concrete will, once it's driving down, whether it has rock or concrete underneath there, the chains will engage, forming a compaction surface. This is a little bit about the GCC construction installations, and you can see that there's a pressure to volume relationship here. As the mandrel is inserted into the ground and concrete is pumped, you can see during the drive that the compression or the air pressure goes up. So as it's being driven from one side, going from left to right, when you're driving it in and you're continuing to pump concrete within the mandrel, you'll see pressure start to increase. On the alternate side of things, when you extract the mandrel, which means you're extracting volume of concrete down here at the bottom, you'll see the pressure go down. So that's the pressure to volume relationship that we're seeing here. You'll then add sequential bulbs or sequential strokes going up and down to form a series of bulbs down here at the bottom, which will act similarly in methodology of a bell drill shaft. If you think about a bell drill shaft, what it's doing is it's spreading the load out over a wider diameter or a wider surface area. These are doing the same thing by expanding a base down here at the bottom, using pressure and volume to calculate what the bearing surface looks like down at the bottom, using the volume of concrete pumped and the air pressure that's applied or reduced. Once the bottom bulbs are constructed, then the mandrel will withdraw at a constant rate, pumping concrete all the way to the surface. So it's an expanded base down here at the bottom and then constant rate of withdrawal going all the way to the ground surface. At no point in time will the volume get below zero. It will always stay positive until it gets to the ground surface. As far as what a typical detail might look like on a GCC project, you'll see here, you have a concrete ring footing, a granular pad on just underneath the ring footing. This allows for a shear break between the ring wall and then the tops of the geoconcrete elements. You may see a widened top at the top of the GCC elements. This may be a load transfer mechanism, or maybe just to attract more load so that we can load these things up to a little bit more because of the high loads. But then you'll have the shaft that applies the bottom of the bulb to a specific elevation. This can be to bedrock, a dense sand, something like that, or to a competent bearing stratum. Why Geopier? This is a question I get asked a lot. And for this particular application, I'd say of the things that are mentioned on your screen, the thing that matters the most is experience. We have experience with these heavy loads, and that matters. It matters to make sure that you not only have a proven track record of great settlement control supporting these heavy structures, but just to make sure that we're in lockstep with you, that we understand all the components of your project, we understand the soil conditions, and we're in lockstep with you to make sure that at the end of this, we are delivering a solution for your grain bin that matters, that meets your specifications, that performs the way that you would like it to. And that's what we have a proven track record of. And that's been important to every project that we work on. And it's important to, it's what gets us out of bed in the morning. We want to make sure that we do what we say we're going to do, and that's what matters. But there are several people that can help you throughout the United States and the world, actually, that can help you vet a Rand aggregate pier system for your project. There may be a little bit of information that you may need to provide them, whether it be the geotechnical report with boring logs and a little bit of preliminary information about what your project is going to look like. But it's beneficial to let them know as early as you can within the process so that you can understand what budget may be associated with a solution like that. Even though it may be written or not written in the geotechnical report, we can help you with that. So there are ways that you can get in contact with us. If you go to geopier.com, you can see a feasibility portion on the left-hand side there, and it's just a little bit of contact information to enter in. That's it, and someone will contact you. With that, I'd just like to say thanks everyone for attending. Thank you for allowing me to share a little bit of the experience that we have with this and our understanding of this system.